Good morning, ladies and gentlemen. In the background of this picture, you can see something from the country and from the area I'm from, where it's much colder than it is now in Vienna right here. And we will be discussing a little bit about this tree right here. So, what I want to talk about is the following. I want to introduce emergent ecosystem properties. I want to say something about our idea, what resilience is, how we can distinguish resilience and adaptability, and then I can show you a lot of amoeba diagrams from different case studies, and in the end there will be some questions and some concluding remarks. So let's start with this word emergent properties. What are emergent properties? We all know this wording, the whole is more than the sum of the parts, and these emergent properties are the difference. They are not possessed by the components of a subsystem alone, but they are consequences of the interactions between the subsystems or between the parts, and therefore they are not immediately deducible. If you know something about the parts, you still don't know something interesting about your system, for example, about your ecosystem. And we have to distinguish these emergent properties from collective properties. Within the group of emergent properties, there are many hierarchical distinctions which are basing on important scale distinctions. There we have global, thermodynamic, or computational properties. And the interesting emergent properties are the evolutionary properties, which are basing on self-organized processes. When they appear for the first time, it's very surprising. That's why emergent properties always are correlated with something new. But they are also valid if they come in repetition. So what we will be talking about in these next 15 minutes will be secondary emergent properties, and from our viewpoint, resilience is one example for such a secondary emergent property. In a paper which I've been writing together with Søren Nielsen, we have found out that self-organization is an important consequence of emergent properties, but on the other way around, emergent properties are important consequences of self-organization. So these things are correlated. Therefore, one further slide about self-organization. Maybe you have already very often seen this slide where we have a Gedankenexperiment with different gas molecules in different chambers. We are opening the chambers, and then we come to thermodynamic equilibrium. And the wonderful thing in open systems and in living systems is that in dissipative structures, there is the possibility that self-organized gradients appear. So self-organization is the spontaneous creation of macroscopic structures from microscopic disorder, or we could also say it's the formation of gradients. Now, what does this all mean for ecosystems or for the question we are discussing? What does it mean for resilience? And now I come to a repetition of the nice things which Brian has been telling us. They are consequences of self-organized processes. So if we look at the time axis on the x-axis and at specific ecosystem properties, which we call orienters, then we will see that there is an optimizing behavior which can be found very often, and there is some sort of an attractor state for these different ecosystem indicators. Brian has already shown you how this works in successions, so we can look at some examples, and what you see here are different ecosystems with different levels of complexity, and during this development there are more components. The components are more different, they have more interrelations, and these interrelations are more different, and they are more and more nonlinear. So during that development we have an increasing connectedness and an increasing complexity. There are many potential indicators which we can use to measure these sizes, and Brian has already proposed some, so I can go through these lists very quickly. We can look at the structure of ecosystems. We can have a look at thermodynamic orienters like exergy or emergy or entropy productions, for example. We can distinguish different ecophysiological orienters. So if these systems are becoming more and more complex, the loss is reduced, the flux density ascendancy is increased, cycling efficiency are getting higher. And this has specific consequences also for the structure of the biotic community. The diversity is getting higher. We have different species coming in, and there are more and more complicated systems of gradients. And in the end of this series, of course, there are also a lot of network theoretical orienters like the indirect effects, the resident times, network homogenization or synergism or utility, which behave in this way. So there's a steady development and a steady growth towards this state of maturity. And before the resilience debate started, this was the end point up to which ecologists were thinking. They were thinking up to maturity, and they thought this is the final stage and this is fine. But maturity is correlated with a lot of risks because of the high complexity, the high connectance and mutual dependence, because of the high energy demand for maintenance, the low flexibility and the brittleness, which is also optimized in these system states. So if we take another look at this development, then we can say, yes, there is this slow development towards this maturity state, starting at the pioneer stage. We have the creative destruction, and now the question is, where is the arrow to the other side? It's at the wrong place again. But we can find some arguments why we can put it here. So this could also be a very nice discussion. And then we can introduce resilience as we understand it. Here we have the usual dynamics of a certain system. The disturbance is coming, and if the system is able to return to the basin of attraction, then we can talk about resilience, and we can indicate it on the one hand by the amount of disturbance which is necessary to disturb the system, or by the residence times or the return times. So we have introduced another point. If we look at this resilience, then it tells us the system is able to return to the previous domain of attraction. But if we look to the development of a system, then it is also changing these domains of attraction. So if we look at longer time scales, so this would be the observed time scale over there, then we will have another sort of development, and therefore we would like also to talk about adaptability, saying that a system has a high adaptability if the sum of all disturbances and changes in the attractor domains do not reduce the system's degree of self-organization. And we can measure this by some ecosystem integrity values, or, for example, by ecosystem services. This would mean that within that well-known drunken 8 figure, we can say resilience is correlated to the behavior within that domain of attraction, and adaptability would tell us something about the long-term behavior and about the question whether the system is able to optimize these emergent ecosystem properties on the long term. Okay, 10 minutes. Now I will take you for 10 minutes to northern Germany once again, and I want to show you some case studies from this area, and we will move to the eastern part of the Bundesland Schleswig-Holstein, where we have the Bornhöved Lake District, and within this Bornhöved Lake District we have several lakes, and there's one river called Alte Schwentine, which is flowing through this area, and we have been concentrating with measurements, modeling activities, ecosystem research activities on the watershed of this Lake Beilau right here. And there was a special research area with forests in the northern part and arable land in the south. We have been measuring many, many different data, and we have tried to aggregate them, for example, to say something about the environmental target or guideline ecosystem integrity. Now we come back to self-organization and so on. An ecosystem has integrity. This is the way James Kay has defined it. If it retains its complexity and the capacity for self-organization and sufficient diversity within its structures and functions to maintain the ecosystem's self-organizing complexity through time. So we can measure the ability of the ecosystem to increase its complexity for self-organization. And there are many overlaps between this integrity definition and some definitions of resilience. So, for example, as Walker and colleagues have said, resilience includes the capacity of a system for self-organization. Or we can also read that resilience can be indicated by the trend to maintain ecosystem integrity or by the degree to which the system is capable of self-organization. So, in fact, there are many, many overlaps, and we have tried to find indicators that represent an ecosystem as a whole by a minimum amount of values. You can see we have been choosing different gradients, different compartments of the network, and come to this proposed indicator set. Now I will use this indicator set to show you the difference between these two ecosystems, the arable land and the beech forest. In the year 1900, both of these ecosystems have been managed in an identical way, and then things have been distinguished for 100 years, and we can now have a look at what's the difference, what has been coming out. And we are looking at things like the exergy capture, the amount of energy the system can take up, the entropy export, biodiversity, heterogeneity in the system, the storage capacity, the ability to avoid nutrient loss, biotic water flows, and metabolic efficiencies. All these things are orienters, though usually they are optimized in ecological successions. And now we can say the beech forest has 100%, and our maize field is then looking like this. So we can see the exergy capture, the gross primary production is optimized by the farmer, and all the other, the important environmental compartments of integrity are reduced. With these indicators, we can say something about productivities, efficiencies, diversities, or storage complexities, storage capacities. And they also tell us something about the developmental duration of such an ecosystem. So the higher the values, usually the longer it takes to get there. So if we come back to these orienter pictures, there have been two totally different systems developed out of these old arable land ecosystems. And if we use these ideas of potential functions, then we can say that the strengths of the natural constraints are quite low in the case of the agricultural ecosystem, but we have very high strengths in these potential curves concerning the beech forest. And the domains of attraction are very different due to their sizes. And we can say that the forest ecosystem has a high self-organization, thank you very much, structure with an internal control, while the agro ecosystem, of course, has a very high external control. And if we put many, many of these different things together and look at the definition of engineering resilience in the end, because this can be very nicely measured, then you can see the last row here. We have long return times to get back to our beech forest and very slow ones to get back to the arable land. So the hypothesis is that we have low resilience in the beech forest and a high resilience in the agro ecosystem. Now we will move a little bit further to the lakeside because it's so hot outside. I thought it's nice for you to have some neighborhood to the water. And we will be moving through many of these different ecosystems at the shores, the wetland ecosystems, and we will be once more using these integrity indicators like species diversity. We are looking at primary production, microbial soil respiration, at metabolic efficiencies, and so on. And for us, it's very important to state this point that we define the identity of an ecosystem not only by the species we find there, but also by the values they can contribute concerning these functional and organizational indicators. So what you can typically find in northern Germany is a retrogression, a degradation of ecosystems where you start with a wet alder, you move through different stages of these disturbances like drainage, eutrophication, grazing, mowing, or plowing, and in the end, you end in a wet grassland, which very often is very intensively drained. So if you want to have an idea what we are talking about, then you can see that these ecosystems are really losing a lot of their biological integrity and their structural characteristics. Now, if we take into account that the final stage of this degradation of these wet grasslands is taken as a reference as 100, then what is going on during the degradation is the following. This is the nature-near system. You see, 180% of the plant species are available. The low carbon balance values here, for example, say this is a sink of carbon. This is also a sink of nitrogen. And many of these processes of nutrient loss are rather small in these ecosystems. So as we are now including eutrophication and increasing drainage, we are in the end in this system. And what we can say is, yes, this system has gained a lot of primary production. Look, this is a very big difference right here. But it has lost the structures, it has lost its efficiencies, it has lost the metabolic efficiencies, the gradients are degraded, and it has turned from a landscape functional sink of nutrients and of carbon to a source of CO2 due to mineralization. So the question is there a way back? Strong measures can help. We have to re-wet the whole system, or we have to take away all the soils and start the whole succession once more from the start. So you could say, well, this is very nice. We have different wetland ecosystems which become somehow structural order cars again. But if we look into the details of these systems, for example, to these three indicators, the mean species number, net mineralization, and the nitrogen balance, and we apply this to these other alder cars, then you can see that there are really very, very big differences between those ecosystems. And in fact, from the functional viewpoint, also all these restored ecosystems very hardly come back. So we have a reversible retrogression in one case. We have irreversible retrogressions in the other cases because we do not reach the identity again. And in one case, there are very extreme measures necessary. For the first way, we need about 40 years. For the second possibilities, we need about 100 years. And for the third one, we need an enormous amount of money. And therefore, this does not happen very often. So looking at this whole series once more, we have a decrease of ecosystem integrity during that retrogression. In one case, there's the reversible change. All the other systems do not reach the old size again, so there's only one resilient possibility. But we have the possibility of returns. If we invest enough money, we can build such constructed ecosystems very easily. So let's come to the end. Once more, giving an overview of these retrogression and resilience studies, we can say the whole retrogressional succession ends in a state where there's no resilience, no adaptability. We have one resilient pathway where abandonment leads backwards. If we have these restoration measures, then on the one hand there are small steps possible, so these single scale changes are resilient, but they're not adaptable. And if we really move these systems until to the end, there's neither resilience nor adaptability. But if we look at this whole investigation, then there are more questions than answers. So if you want to make interpretations concerning resilience, you have to be very specific concerning the question, what's the target system, how it is defined, which is this identity, which is the level of integration, the scale you're working on, which are the indicators. Do you look at structural or functional items? What exactly is the disturbance, which is your temporal scales? And do you include management measures to define resilience? Or do you only rely on self-organized processes? So if we come to the nearly very end, we can say, okay, resilience and adaptability are emergent properties. They change with developmental stages. While resilience is related to a return to an old attractor, adaptability considers the future-oriented dynamics of self-organization. Simple systems can return easily to their attractor, and resilience and adaptability valuation can be very ambiguous. Therefore, the conditions have to be defined very, very strictly. Coming back to the, yes, you said we have to answer these questions. What is the evidence of resilience? Well, it's a descriptor of system dynamics. It's a reference for the steady state dynamics in our system. And our proposal is to think about a supplement of this resilience approach by the adaptability idea for long-term processes. What are the threats? In our cases, it was land use, drainage, and it's also climate change, because due to these wetland dynamics, the whole watershed has become a source of CO2, while in the times before it has been a sink. And this is also valid for nutrients. What role do networks play in the design of decision-making structures? Well, they are the basic components of our integrity, and they are very important ecosystem properties. Within the networks, we have these important regulations of inputs, flows, storages, and outputs, and they are the basis for our integrity indicators. Yeah, I've used a long time. I'm grateful that you have been listening to me, and we can come back to the winter time in Kiel and to the question, well, this guy, was it resilient? Brian knows this area. We've been walking along there very often. You can see the first one has already left us a year later. Then it was starting to walk, and now it's looking like that. So nothing is permanent but change. Thank you for your attention.